Send a powerful electric current through a solid metal cable, and the surrounding space fills with swirling, invisible waves of magnetic force. In 1820, Danish physicist Hans Christian Ørsted proved these hidden fields existed by watching a simple compass needle deflect when placed near a live wire. To map the strength of that field, physicists relied on the Biot-Savart law. The equation calculates the total magnetic field by summing up the microscopic field contributions from every tiny segment of a current-carrying wire. It requires integrating complex vectors, often resulting in a grueling calculus problem. French mathematician André-Marie Ampere recognized that the brute force integration of the Biot-Savart law wasn't always necessary to find the answer. He realized that if the physical setup possesses perfect spatial symmetry, like a uniform, perfectly straight wire, the complicated vector math collapses into highly predictable, simple geometric relationships. Ampere's law operates as a mathematical shortcut. By exploiting the inherent shape of the magnetic field itself, you can bypass the tedious calculus and solve complex physical systems using basic algebra. The law relies on three specific geometric components: an open surface, a boundary line that encloses that surface, and the electric current piercing through it. To evaluate the magnetic field, we draw an Amperian loop. An Amperian loop is a closed imaginary boundary path chosen to tightly match the physical symmetry of the magnetic field we want to measure. Ampere's equation dictates that summing the tangential magnetic field along this entire boundary, a process called a line integral, exactly equals a constant value, mu0, multiplied by the total enclosed current. If we align our Amperian loop with the system symmetry, morphing the boundary into a perfect circle concentric with a straight wire, the magnetic field remains perfectly constant along the entire edge. The terrifying integral dissolves. The magnetic field multiplied by the boundary's circumference equals the constant times the enclosed current. We establish the positive or negative sign of that current using a right-hand rule. If you curl the fingers of your right hand in the direction you traverse the boundary loop, your thumb points in the direction of positive current flow. The Amperian loop serves as a mathematical net. When you construct a boundary that mirrors the magnetic field's natural symmetry, the geometry isolates the variables, allowing you to solve for the field effortlessly. We apply this method to a real-world object, a thick, solid cylindrical wire with a specific radius, A, carrying a steady, uniform current, I. Looking down the cross-section, the current appears as a grid of uniform dots coming toward us. We draw an Amperian loop at distance r, greater than radius a. This completely encircles the conductor, capturing the total enclosed current, I. We map these values into our equation. The magnetic field B times circumference 2 pi r equals mu0 times the full current. Dividing by the circumference isolates B. With r in the denominator, the field strength outside the wire decays inversely as you move away. From outside the copper boundary, the wire's physical thickness does not affect the calculation.
The physical system behaves exactly as if all the current were condensed into a single, infinitely thin thread at the dead center. The math behaves differently when we cross the outer skin of the copper and investigate the magnetic field inside the solid mass of the wire. We construct a smaller Amperian loop. This time, our distance r is less than the wire's total radius, a. This boundary no longer encompasses the entire cylinder. It traps only a fraction of the total current. Because the current is distributed uniformly, the trapped amount scales precisely with the enclosed area. We calculate this by multiplying the total current I by the ratio of the areas, the internal radius squared divided by the total radius squared. We substitute this fraction into Ampere's law, and the radii partially cancel out. The result shows that inside the solid wire, the magnetic field strength grows in direct linear proportion to the distance from the center. At the precise geometrical center, where distance r is 0, the enclosed area shrinks to 0. With no current trapped inside the boundary, the generated magnetic field is 0. Moving outward through the copper captures more current, which overpowers the expanding distance to build a stronger field. But once you breach the surface into empty space, no new current is added, and the expanding circumference stretches the existing field thinner and thinner. By combining the internal linear growth and the external inverse decay,
we construct a complete mathematical profile of the wire's magnetic force. Plotting the magnetic field B on the y-axis against distance r on the x-axis, we mark the wire's boundary at A. Field strength rises linearly as we travel outward through the metal. Once in empty space, it decays along a sweeping curve. The absolute peak of the graph sits exactly at distance A. A solid, uniform wire exerts its maximum magnetic force right on its outer skin. When Ørsted first mapped the magnetic deflections of his compass in 1820, the physical forces pushing against his needle were governed by the exact geometry of this downward curve. The graph visually proves that the behavior of the magnetic field depends entirely on a single condition, whether an expanding boundary continues to enclose new current or simply retreats into empty space. Ampere's law allows us to easily calculate magnetic forces inside thick cables, tightly wound solenoids, and other highly symmetrical systems where direct calculus is highly inefficient. Decades after Ampere published his geometric approach, James Clerk Maxwell integrated these rules into a unified framework, eventually proving that light itself is a propagating electromagnetic wave. Today, analyzing physical symmetry remains a primary method for physicists looking to calculate the precise mechanics of complex invisible fields. By framing a physical problem around the geometric constraints of the universe, the heavy mathematics simplify and the underlying rules become clear. Solving complex physics requires analyzing the shape of the system, choosing an appropriate boundary, and allowing nature's inherent symmetry to reveal the answer.